Hello, everybody. Thank you very much for joining Paul and me this afternoon, or earlier in the day if you're in the States. I'm very, very excited to have my friend Paul Halpern here talking about his new book, The Quantum Labyrinth, Richard Feynman and John Wheeler, Revolutionized Time and Reality. This is a book. It's an absolutely wonderful book, and I highly recommend it. In fact, I recommend all of Paul's books. They're fantastic. So Paul is Professor of Physics at the University of the Sciences in Philadelphia and has written lots of wonderful science books and has been on The Simpsons, which I will ask him about later for you. And I will straight away hand over to you, Paul. Thank you very much for coming and giving the talk.
Well, thank you very much. I'd like to thank Lisa Tenzin-Dolma for inviting me to this program. It was a great idea, and I really look forward to it. So I'd like to start off with a picture that everybody has seen, Albert Einstein. Everybody has heard of Einstein. His face is familiar to everybody around the world on T-shirts, posters. So if you see this face, you know exactly who it is. But not everybody has heard of Richard Feynman and John Wheeler. We see a picture of Wheeler on the left in a characteristic pose. He did a lot of interviews on the BBC and elsewhere, so that's a picture from one of his interviews. Wheeler is not quite as famous as Feynman, but Wheeler also was in a lot of TV programs, and he was in films, including the film A Brief History of Time, which was about Stephen Hawking. And Wheeler was very vocal about his ideas about time and the history of the universe. So he was also a popularizer in his time. Wheeler and Feynman are considered two of the best American theoretical physicists of all time, certainly in the 20th century. There were a lot of great experimentalists then, but not so many theorists from the United States. We see a cartoon that was done for a review of my book in the Wall Street Journal, and I really love it. You see Wheeler and Feynman in characteristic poses, Wheeler with his blackboard and Feynman kind of with a kind of perplexed expression on his face. Many people remember Feynman, if you think back to the 1980s, from the Space Shuttle Challenger Disaster Commission. He was invited by President Reagan to serve on the Rogers Commission to investigate the shuttle disaster back in 1986. And Feynman had an opinion that differed from the rest of the commission. He was much harsher in terms of his judgment of the companies making the shuttle. And during the congressional hearing, he took out an O-ring, which was part of the shuttle, and dipped it in ice water and showed how it was not resilient to the cold. And that was key to his finding that the shuttle was designed poorly, and that's what led to the disaster. Feynman shared the 1965 Nobel Prize in Physics, along with Julian Schwinger and Tominaga from Japan. We see some pictures from the Nobel Prize ceremony, including, in the bottom, we see Feynman with the Queen of Sweden. You see how delighted he was to participate in the Nobel Prize ceremony from the expression in his face. Feynman was known as much for his wild antics and unconventional personality as he was for his physics. We see some pictures of him. On the left, we see a picture of him with bongo drums, which was something he loved virtually his whole life, starting in his time in Los Alamos. We see in the upper center, we see a picture of him, or painting actually, by Sylvia Posner. It's a painting of him at a party where he was dressed as a Himalayan monk. In the bottom is him at a commencement ceremony at Caltech. And finally, on the far right is a picture of him in the role of the chief of Ballet High, which he participated in the Caltech musicals, and that was from the musical South Pacific, directed by Shirley Marnius. And the photo has a bit of a history because that was taken only a few weeks after a life-threatening surgical procedure where he had cancer and he needed major surgery, and he lost more than 100 pints of blood during the procedure, and there were 100 pints of blood donated during the procedure, I should say, by students because he was losing blood, and he arrived at the musical much to the surprise of the Caltech community, and participated in his part where he needed to mutter some commands in Tahitian, which he had to learn Tahitian for, and command the drummers, and students stood up and gave him a standing ovation because they were so shocked and surprised and delighted to see him perform so soon after his major surgery. Wheeler was much more conventional in his personality. We see him always with a suit and a tie. On the left, there's a picture of him with American President Lyndon Johnson, and he won the Wheeler Prize, the Fermi Prize, and that's President Johnson awarding him the Fermi Prize. Yet in his ideas, he was far more unconventional than Feynman. We see him with a blackboard demonstrating things like wormholes and black holes. He loved to fill a blackboard and then explain it to an audience with all sorts of wild pictures about his very zany ideas. So inside, he was much wilder than Feynman, even though he had the veneer of being a very conservative person. From Wheeler's clever mind came ideas such as wormholes, black holes, and the idea of the participatory universe, which we see in the picture on the right with the eye looking backward in time. And the idea is that consciousness can steer the early universe through a quantum measurement and affect the way we are today. Throughout his long life, Wheeler would write down his ideas in a notebook, and these notebooks are preserved at the American Philosophical Society. Here's a painting of Wheeler on a beach in the U.S. state of Maine, sitting on a rocky beach and thinking about ideas and writing them down. So let's look back to 1939 when their friendship began. Wheeler was a young physics professor. He was only 28 at the time, and Feynman was 21, and Feynman just started at Princeton University. Wheeler was assigned Feynman as a teaching assistant by pure chance. Originally, Feynman was supposed to be assigned to another physicist, Eugene Wigner, but Feynman was switched to Wheeler, and it was serendipity because the two of them clicked immediately. Feynman was already well known as a brilliant graduate of MIT. Feynman had made a name for himself and was already in newspaper headlines. Back in high school, he won a math competition, so that won him a New York Times headline. And we look at some of the other headlines, including when he was in the dean's role at MIT, the dean's honor roll, and he also scored the highest in the United States at in a mathematics competition called the Putnam competition. So that gave him a reputation already at the age of 21 as being a math genius. The first meeting that Wheeler had with Feynman, Wheeler put a fancy watch on the table, a pocket watch, because Wheeler was interested in seeing how efficient his meeting was with students. So he wanted to dole out his time. He wanted to make sure that he spent time doing everything he needed to do, including teaching, meeting with students, research, and so forth. He put the pocket watch on the table, and then between that meeting and the next meeting, Feynman went to a store, bought a cheap watch, and as soon as Wheeler took out his pocket watch, Feynman took out the cheap watch, put it on the table right next to it, as if a he was making a countering chess move. The two of them looked at each other. Feynman, Wheeler laughed at Feynman. Feynman started laughing too, and a friendship was born, and they became lifelong friends from that moment on. The two were really quite an unusual pair. As mentioned, Feynman was more casual. Wheeler always wore a suit, and yet Wheeler's ideas were far more wild than Feynman's were. Feynman had a very thick working class accent from Queens, New York. He liked to go bar hopping. He played the bongo drums. Yet in his physics, he was far more conservative. He only believed what could be proven. They only had a brief window of opportunity to work together at Princeton. Between the start of World War II, September 1939, and the American entry into World War II, which was December 1941. So in that brief period of time, less than 2.5 years, they developed a project called the Wheeler-Feynman absorber theory, which involved looking at how electrons interact with each other. And Dirac, the great physicist Paul Dirac, had developed a theory of electrons involving interactions with another particle called photons. And in that theory, an electron would emit a photon and another electron would pick it up. But the main problem with Dirac's theory is that if you calculate it, mathematically you end up with an answer of infinity. And that would not do for a physical theory to have infinite answers. So what happened is Wheeler and Feynman got together and said, well, what happens if we eliminate the middleman? If we eliminate the photons, well, we can get finite answers. And that's what they did. And the only trick to their theory is that electrons could interact directly as long as they send signals both forward and backward in time. So that became the Wheeler-Feynman absorber theory, which involves signals sent backward in time as well as forward in time. So in other words, if you jiggle an electron, it's going to send a signal to another electron, but also the second electron is going to send a signal backward in time that hits the first electron instantaneously, which leads to finite terms in their theory. Very unusual, but it worked. One day, Feynman was in his dormitory room, and Wheeler called him on a phone and said to him, what if not only do signals go backward in time, but what if electrons themselves go backward in time? And suppose all the electrons in the universe are the same particle. Suppose one electron zigzags forward and backward in time, and every time it moves forward in time, it's a negative electron, a standard electron, and every time it moves backward in time, it's a particle called a positron. Now, a positron is a positive electron, and this introduced the idea that positrons are really electrons moving backward in time. Well, this is a very strange idea. It's almost like the film Back to the Future 2, and if any of you have seen that film, it involves time travel. And in Back to the Future 1, a character named Marty McFly goes backward in time to the 1950s. In Back to the Future 2, Marty McFly needs to return to the 1950s to correct some mistakes in the past. So there are two versions of him in the same era. Well, in the Wheeler-Feynman idea, or Wheeler's idea about the one electron universe, there would be an infinite or indefinite number of electrons in the same era, because electrons would keep zigzagging backward and forward in time. So it'd be almost as if in the film, Marty McFly kept returning to the 1950s and doing different things, and eventually the 1950s will be filled with, you know, thousands or millions of Marty McFlys. Well, here the universe, according to Wheeler's idea, is filled with so many electrons that we think there are many electrons, but really they're all the same electron. Much later in life, at a diner in California, Feynman would tell physicist Kip Thorne, you think Wheeler's gotten crazy in his later years? Well, he's always been crazy. And that remark referred to the idea of the one-electron universe, which Feynman explained to Kip Thorne. And then Feynman added, well, you need to distill the ideas from Wheeler, the good ideas, from the crazy ideas, and then you get good physics. And that was Feynman's gift, to look at Wheeler's ideas and be able to distill the best ideas from Wheeler's crazy ideas. At the time of Feynman's research, he was engaged to aspiring artist Arline Greenbaum, who he would marry in 1942. Now, when they got engaged, unfortunately, Arline had tuberculosis, which at that time was incurable. And Feynman's parents advised him not to marry Arline because they were worried about her health. And her health was in peril at that time. But Feynman loved her and decided to take a risk and marry her because he felt like he gained so much from their relationship, that she was his muse. He was inspired by her art. She also played piano. He was inspired by her music. And they also loved to share stories. And Feynman would share his adventures with her, and she would get a good laugh out of it. And they were a great couple together. Now, when they got married, sadly enough, they married at a courthouse, and immediately Feynman had to take her to a tubercular sanatorium, which was the only way that tubercular patients could be treated at that time. It was called the rest cure for tuberculosis. So he dropped her off at a sanatorium and would have to visit her there. Now, Wheeler taught Feynman the idea of diagrams being used to visualize physics. And then through Arline, he also began to appreciate the aesthetic quality of art. So combined, that led Feynman to develop his idea of Feynman diagrams, which are still used today. So we see on the right a picture of a typical Feynman diagram involving electrons, which are represented by the letter E. And then the letter in the middle is the Greek letter gamma, and that represents photons or light particles, which Feynman eventually had to add back into his theory. So that's a typical Feynman diagram. Later in life, Feynman was so proud of his diagrammatic approach that he bought a painted van that was painted with, specially painted with Feynman diagrams. And he was very proud. He would drive to beaches in Southern California, and he was happy when people would ask him, what are the squiggles on your van? And he would explain Feynman diagrams and explain that he was Feynman. He was very proud of that. Years later, the van was restored and appeared in the TV series The Big Bang Theory. So that's, and at the end of the episode, a replica of the van was blown up. I was pleased to hear that it wasn't the actual van, but a replica of the van was destroyed at the end of the show. So Feynman's approach not only involved diagrams, but also had the unique idea, which gave my book the title, The Quantum Labyrinth, the idea of time as a labyrinth. So we see here his idea of sum over histories, which was dubbed so by Wheeler, that electrons not just interact a single way, but in the quantum version of his theory, they interact many different possible ways simultaneously. So we see here electrons interacting many different ways at the same time. This is similar in some ways to the short story The Garden of Forking Paths by Jorge Luis Borges, which was strangely enough written around the same time, although there's no evidence that either of them influenced each other. And in that story, characters interact in different ways at the same time. From 1942 to 1945, both Wheeler and Feynman needed to take a break from the research to join the Manhattan Project, which was the project to build the atomic bomb in the United States. And we see a cartoon of Feynman during the Manhattan Project, and his big hobby at that time was safe cracking. He would try to crack open safes, he would pick key locks, and then he would show people the secret documents to show how unsafe or insecure they were. And even when physicist Edward Teller said, well, I have my documents in my desk drawer, there's no way you can get that open, he would reach into the back of the desk drawer and get the documents from the back. So he would show Teller that he managed to pick the desk as well and get the secret documents. So he was very clever, and they would go back to Arline, who was in a sanatorium at that time in New Mexico, and they would both laugh at some of the antics he would pull. Now, sadly enough, 1945, Arline died of tuberculosis. Shortly before the beginning of 1945, John Wheeler's brother was killed in World War II. Feynman witnessed the Trinity test, which was a test of the atomic bomb, and soon thereafter that year was the dropping of atomic bombs on Hiroshima and Nagasaki. And Feynman had very little reaction to the dropping of the bombs, probably because in some ways he was emotionally deadened because of Arline's death. But then later it hit him that of the horror of the bombs, and he had regrets that the bombs were developed. It hit him when he was in a restaurant with his mother the following year, and he imagined what would happen if New York City was hit by a bomb, and how many people would be killed if that happened. So he had regrets, and he never pursued military research again. Wheeler, on the other hand, felt that if the bomb had been developed earlier, perhaps his brother's life would have been saved. So Wheeler continued with military research and joined the hydrogen bomb project because he felt that if the atomic bomb had been developed sooner, perhaps his brother Joe's life would have been saved because the war would have ended earlier. So Wheeler was heavily involved in the H-bomb project, which was stimulated in part because of a spy, Russian spy named Klaus Fuchs, who was actually a friend of Feynman's when Feynman was working in Los Alamos. Feynman would borrow Klaus Fuchs' car to go visit Arline, not knowing that Klaus Fuchs was a spy. But then it turned out that Fuchs was a spy and had given the Russians secret information about the atomic bomb. And that led to the Americans developing a hydrogen bomb, and Wheeler was involved in that project. Once the H-bomb project was winding down, Wheeler got in trouble because he brought secret documents about the H-bomb project on a train, and he fell asleep, and when he woke up, when he was in the train station in Washington, D.C., the documents were missing, and they still never have been found. In the process of preparing for the hydrogen bomb, Wheeler likely saw a paper by Robert Oppenheimer, which appeared in the same issue of Physical Review that his own paper with Niels Bohr about the atomic bomb, or about nuclear fission rather, appeared in. And that likely led Wheeler to become interested in Einstein's theory of general relativity. Oppenheimer's paper was about the collapse of stars, which later became called black holes, but wasn't known as black holes at the time. Meanwhile, Feynman received an offer to work at Cornell. He received many job offers, but took the job at Cornell University in New York State. And he was very depressed for a time because of Arline and because of the bomb. But then he was sitting in a cafeteria and a student threw a plate, and he analyzed in his head the dynamics of the plate, calculated the rate of spin, and that led him back into becoming interested in physics again. He thought, well, I still have the spark to be able to calculate physics. So that led him into his Nobel Prize winning work. When Feynman wanted to let off steam, he would play the bongo drums. That was a lifelong pursuit. He briefly got married again. His second marriage only lasted for 4 years. It was doomed from the start because his second wife didn't realize that he would spend so much time on calculations, and she didn't like his calculus, and his drumming drove her crazy. And in newspaper accounts of their divorce, they noted that she complained to the judge about that he did math all the time rather than speaking to her, and the drums drove her crazy. And the punchline of the newspaper articles were, she got alimony, property and cash, Feynman got the drums. They say third time is a charm, and Feynman was lucky with his third marriage to a woman named Gwyneth, who was an English woman that he met when he was at a conference in Geneva. And strangely enough, he didn't invite her initially to marry him, but he invited her to become his housekeeper. And she was his housekeeper for a year in California, but then they fell in love and she married him. You see a picture of them at the Nobel Prize event in 1965, and you see from the look on his face how happy he was in his third marriage. Now, Feynman's best man for their wedding was an artist named Juri Zorthian, an Armenian artist who was quite innovative. And Zorthian was a little bit of a wild character. They met when Feynman was at a party. He was playing bongo drums. Zorthian took his shirt off, shaved, sprayed himself with shaving cream, and started dancing around wildly. And Feynman thought, hey, that's my kind of guy. And they became lifelong friends. And Zorthian was his best man. And Zorthian taught Feynman how to paint. Feynman, in turn, was supposed to teach Zorthian physics. But Zorthian didn't really learn much physics. But Feynman became quite an accomplished amateur artist. So you see here a couple of Feynman's paintings, which he even sold at some point under the pseudonym Ofe, which was a little bit of a play on Feynman's name, and also a French word. Feynman would sometimes fill pads with both equations and his sketches. So we see here an example of that. And another of his hobbies was dressing up for plays and parties. He was involved in the Caltech musicals, and also he would go to parties that his student Al Hibbs would run, April Fool's parties. And the parties would always have a theme. It would be some kind of question, and Feynman would dress up, and other partygoers would dress up to answer the question. So on the left, the question was something like, dress as your favorite religious figure, and Feynman dressed as a Himalayan monk. The middle one was dressed as a mythical character, so Feynman chose God, which was quite amusing. But people thought he was dressed as Moses, but he told people at the party, no, I'm really God. And Al Hibbs, who was running the party, said, yeah, he always thinks he's God. And then the one on the right is when they said dress as a royal figure, and Feynman dressed as Queen Elizabeth. In the 1950s, as mentioned, Wheeler became interested in relativity, and he also managed to get Feynman interested in that to some extent. And his look at Oppenheimer's black hole paper led him to believe that that the universe is not really all electrons like he once thought, but is shapes, geometric shapes. So Wheeler started to think that all is geometry, that all is shapes. And at one point, he brought his class to Einstein's house. Einstein lived in a neighborhood, and Einstein at one point spoke to his class at Princeton, which they had to keep secret because otherwise it would attract large crowds. And that was Einstein's final lecture. And at the lecture, Einstein spoke about his things that he disliked about quantum theory, and that proved quite influential, as we'll see. Wheeler also became interested in the idea of geons, which are particles formed of geometry, and wormholes, which are connections with other parts of space. So Wheeler often consulted with Einstein about his wild ideas. So we see a photo of Einstein on the left, the Japanese physicist Yukawa in the middle, and Wheeler on the right, taking a walk in Princeton. Later, a student of Wheeler, Kip Thorne, would develop a larger idea of wormholes, wormholes that are large enough and stable enough for spaceships to travel through. And those are called traversable wormholes. So another student of Wheeler, Hugh Everett, who attended the last lecture by Einstein and was influenced by Einstein's dislike of standard quantum theory, decided to develop a new interpretation of quantum theory called the many worlds interpretation, which is also known as the parallel universes interpretation. And we see here a picture of Niels Bohr, who championed the orthodox view of quantum theory, in the center, and Hugh Everett is standing directly to his right. And Hugh Everett thought that Bohr's idea that every time a person takes a measurement that leads to a quantum wave function collapse is unintuitive, and that actually when anybody takes a measurement, instead of the person influencing the measurement, the universe bifurcates, it splits up into multiple parts, and that the observer also splits, and the observer has clones of himself in each of the different universes. So, for example, in the famous Schrodinger's cat experiment, which we see here, instead of the cat being a mixture of alive and dead until somebody takes an observation, opens the box, and the cat is either alive and the person's happy, or dead and the person is sad. Instead of that, when you place the cat in the box, the cat is alive in one universe and deceased in another universe. So the universe bifurcates, and in one version of the universe, the cat is alive. In the other version of the universe, the cat is dead. And the person observing the cat also has split by then. So when they open the box, the two copies are opening the box and seeing different outcomes. So that's Everett's idea called the many worlds interpretation. Wheeler was very interested in that idea because he wanted to develop a quantum theory of the universe. And with the quantum theory of the universe, it's impossible to have an outside observer. So this was a way of not needing a human observer, but rather having a self-consistent version of reality. Probably Wheeler's greatest contribution to physics was promoting the idea of black holes. He didn't really coin the idea of black holes. He heard that at a seminar, but he loved the idea, he loved the term black holes, and promoted that in his later years. And we see on the right an example of Wheeler's dry sense of humor. He went to a place called Black Hole, Nova Scotia in Canada, and he got a t-shirt, "I've experienced Black Hole, Nova Scotia," and wore the t-shirt while he was looking for black holes and got photographed doing that. And that was his dry sense of humor. Wheeler had many famous students, including Jacob Bekenstein, who solved the great black hole conundrum. The conundrum arose because of the idea of entropy or disorder. Now, entropy means that things tend towards disorder. And for example, if you take a teacup and drop it, it shatters. If you take a teacup full of hot tea and you place ice cubes in it, then they will reach a common temperature, which is a more disorderly state than just having hot tea and an ice cube. An ice cube is a very ordered state because geometrically it's much more regular than having a gas or a liquid. So anyway, if you drop an ice cube in tea or place a glass of ice next to a teacup full of hot tea, basically you're increasing the disorder in the universe. And Wheeler commented once to Jacob Bekenstein that he felt that that was committing a crime by increasing the amount of disorder in the universe. But if you could drop the teacup, which has cooled down, into a black hole, then you would hide evidence of your crime, Wheeler said. Well, Jacob Bekenstein showed that the black hole would increase in area, specifically the area of an imaginary surface called the event horizon, which is the limit of where a light could escape from a black hole. Well, that area would increase, and that would show how the black hole's event horizon increased. That would relate to its increase of entropy. So the area of a black hole's event horizon, which is really the size of a black hole, pertains to a black hole's entropy. And that is the black hole entropy theorem that Bekenstein is very famous for. One of Wheeler's strangest ideas is called the participatory universe, that the universe is the way it is because when we look back at the past, an astronomer taking a measurement of a past is doing a quantum measurement, and that quantum measurement can affect the past. So when you look back at the past, you can influence it, and perhaps the universe is the way it is today because we're measuring it. And that leads to a closed loop, which Wheeler called a self-excited circuit, that by looking back at the past, we're affecting the present, which is a very strange idea. But the missing ingredient there is why we exist at all. And that is the question that occupied Wheeler's thoughts in his later years. How come existence? And he was obsessed with this idea of trying to solve the meaning of life, why we exist, in his later years. And Wheeler called this idea of self-excited circuit, which we can see in this diagram. If you look back in the past, you change the past, that affects the present, which creates consciousness. Wheeler was interviewed once about this idea in the magazine Reader's Digest, a popular magazine, and he got a lot of unwanted fan mail about this idea, which he had to, he couldn't look at all the mail because he got a lot of people asking him about religion and what this meant about God and so forth. And he really didn't want to answer that question. He thought of it more of an idea in physics rather than a theological idea. Nevertheless, he devoted his final decades to probing this question, how come existence? And we see even in 2002, when he was in his 90s, he was still trying to probe this idea. And I had the pleasure of meeting him around this time in 2002, and he still said he was spending his time, his final years, trying to solve this riddle. By the time Wheeler was in his later years, in the 1980s, Feynman was ill with cancer. Feynman, nevertheless, was involved in the Challenger Commission, which we see a picture of him with Neil Armstrong. In 1987, Feynman had the opportunity to witness a famous supernova explosion, and was thrilled to see that because by that time he was very ill and probably knew that he didn't have much longer to live. And in fact, in February 1988, Feynman died. Wheeler survived 20 more years to the age of 96. We see here a picture of Wheeler at the LIGO experiment, which detected gravitational waves. Wheeler was very interested in the detection of gravitational waves, would have been thrilled to know that his student, Kip Thorne, won the Nobel Prize as a group for detecting gravitational waves. When Wheeler died, Freeman Dyson said, the poetic Wheeler is a prophet standing like Moses on the top of Mount Pisgah, looking out over the promised land that his people will one day inherit. He was quoted in Wheeler's obituary saying that, and what he meant is that many physicists today derive some of their ideas from the inspiration of John Wheeler. So for more about Feynman and Wheeler, please take a look at my book, The Quantum Labyrinth, which this talk is based on. And now at this point, I'd be glad to answer any questions about my talk. So that's my talk, and now I'd like to invite Lisa to see if there are any questions from the audience. So thank you.
Thank you very much, Paul. That was fascinating. Does anybody have any questions? Either about today's talk or any questions generally that you'd like to ask Paul? You can type them in the questions panel and I can read them out, or you can ask to speak to Paul directly and I can switch on your microphone. Well, if I start, Paul.
Okay, sure.
About how this book came about. How did the Quantum Labyrinth come about? What brought about the idea for the book?
Well, that's an interesting story because I was invited to supervise a discussion panel after a play in Philadelphia. There was a theater company called the Lantern Theater Company that produced a play about the life of Feynman called QED. And I was invited, first of all, to help with stage directions for the play. So they were doing Feynman diagrams on a blackboard as part of the play, and I had to give advice on how to explain the Feynman diagrams. And then for one of the showings of the play, afterward there was a discussion group, and I was running the discussion group. And then the director of the play said, well, is there anybody who has a Feynman story to tell? And I remembered at that time a couple of stories. I didn't know as much about Feynman at that point as I do now, of course, but I had a couple of stories to tell. And then a gentleman in the audience raised his hand and he said, well, I remember when Feynman came to my house when I was a little boy and juggled some soup cans and showed some physics experiments using the soup cans, meaning tins of soup. And so I was kind of amazed that Feynman came to this gentleman's house when he was a little boy. So I said, excuse me, sir, what's your name? And he said, well, I'm Jamie Wheeler. I'm John Wheeler's son. So I realized at that point that Jamie Wheeler, who's a physician, lives in the Philadelphia area. In fact, doesn't live too far from where I live, and is very active in the Philadelphia area. He was a subscriber to that play series by sheer coincidence, and so that led me to think, well, maybe one could write a book about Feynman's interactions with Wheeler. And I interviewed Jamie Wheeler for the book. I interviewed Jamie's sisters, John Wheeler's daughters, and I also interviewed other people who knew both of them. And I went to the Wheeler archives in Philadelphia and remotely accessed the Feynman archives in California. And that's what led to the Quantum Labyrinth, all the interviews, the archival material. I had some great interviews. One of the last interviews I did was Feynman's director, Shirley Marnius, who remembered what he was like to be an actor, and for the various musical productions that she directed at Caltech. So it was a really fun project to do, and hopefully that shows in my book.
Wonderful! What a great story! Thank you, Paul. I can see there's a couple of questions here. Vince is asking, in your book, do you discuss Wheeler and Feynman's opinions on the physics being done at the time, e.g. string theory, supersymmetry, etc.? I believe, yeah, that's that question. And then there's another one which I will read out in a moment.
Okay, so I briefly comment about Feynman and Wheeler's views of string theory. Feynman had published views about string theory. He was suspicious about string theory. In an interview he did in the 1980s, he said, well, he remembered when in Einstein's later years, Einstein was suspicious of quantum theory, and Feynman said, well, maybe this places me in the same position, but now I'm older, and maybe it's because I'm older, but I really am very suspicious of string theory. It doesn't really seem like it connects very well with experiments. And Wheeler had similar views, and when I interviewed Wheeler in 2002 for a different book project, that was a book project called The Great Beyond, and during that interview I asked Wheeler what he thought of string theory, and Wheeler said that he thought it was a kind of almost like a kind of theology, that it was almost like preachers speaking to their congregations and trying to advance an article of faith rather than real physics theory. And Wheeler said, well, I'd rather that they could investigate how come existence, which is a much more central question, and how come the quantum. He thought that string theory was not really a viable pursuit because it didn't really connect very well with experiment, which I thought was a little bit ironic because not everything that Wheeler suggested connected very well with experiment, but he had a right to those views. So I mentioned that in my book, that both of them were suspicious of string theory.
Thank you. And John has asked, I believe Feynman was very critical of NASA management for forcing the shuttle to launch in cold weather, for which the O-rings were not designed, leading to his famous quote, nature cannot be formed.
Well, yes, Feynman, in the Challenger Commission, he delivered a report that was very critical of the companies that produced the Challenger, more the private companies rather than NASA. But he urged NASA to be even more cautious than it was because even if most of the time the design worked, even one failure was intolerable, and Feynman's advice was taken to heart by NASA because the respect they had for Feynman's views.
Thank you. Does anybody else have any questions? You just put them in the box, and if you'd like to speak to Paul directly, just type that in and I can switch on your microphone. While we wait, Paul, would you like to talk about your appearance on The Simpsons? Because I know that intrigues a lot of people.
Well, so one of my earlier books, about a little more than 10 years ago, was about science in The Simpsons. I took episodes from The Simpsons, such as the one where Stephen Hawking appeared, or that actually he appeared on 3 episodes, and I discussed the physics behind them. And then a few years after my book was published, the director Morgan Spurlock was directing a special called The Simpsons 20th Anniversary Special, which is about how The Simpsons affected our culture, particularly the culture in the United States, although he did do some interviews in Brazil and places like that too. And he asked me if I could do something about the science in The Simpsons. And I spent a few hours preparing experiments, which he filmed, about the science in The Simpsons. And then at the very end, I was in a biology lab, and I saw a jar of a preserved fish in formaldehyde, and I said, oh, that reminds me of Blinky, the 3-eyed fish from the Simpsons episode. Morgan Spurlock said, well, do you want to say something about that? So he filmed me picking up the jar of fish with formaldehyde and saying, well, this fish has 2 eyes, not 3 eyes, and 3-eyed fish are impossible. And that's the part that he used after hours of filming me do physics experiments. He used a bit about me talking about a fish, which, okay, well, why would he include that bit when I'm a physicist? But I was still very happy to be on The Simpsons. So that's my, it's not even 15 minutes of fame. That's less than a minute on that episode, the 20th anniversary special, but I still get asked about that.
Yes, it's great. And it's a very good book. Science and the Simpsons is well worth reading as well, as all of Paul's books are.
Well, thank you very much.
Sorry, Paul?
I said thank you very much.
Oh, it's a pleasure. Do we have any other questions? In the meantime, Paul, your dog is called Kepler.
That's right.
Named after the scientist, the famous scientist.
An astronomer, which inspired a comment when I was taking him on a walk some time ago. I took him on a walk, and somebody stopped me and said, "Well, what's the name of your dog?" And I said, "Kepler." And they said, "Oh, you mean like the scientist who predicted the motion of the planets?" And then sometime later, I ran into the same person, and they said, "Oh, I see you completed a full orbit." So, which I thought was quite clever, because a lot of I tell people that the dog's name is Kepler, and they say, "Oh, what do you mean, Pepper?" And they're perplexed, because usually a dog named Pepper would be, black dog, and he's a red dog, red poodle. But I'm glad that at least somebody picked up on the name.
I love it. June's commented and said, "Fabulous name for a dog," which it is. I think it's wonderful. And he's a very beautiful dog as well.
Thank you. Yes, I posted a few pictures on Twitter, so if you want to see a picture of my dog, just look at my Twitter account and look for the Kepler the poodle, and there's some pictures, not recently, but some time ago.
Lovely. Do we have any more questions? Okay. Well, thank you very much, Paul.
It was a pleasure.
It's been really lovely to listen to you and to see the presentation. Wonderful to see the images in your talk as well about the book, because it really is an excellent book. So thank you very much for taking the time to come and talk to us all.
You're very welcome, and I enjoyed the questions, and it's a great opportunity to speak to an international audience via webinar.
Fabulous, and thank you everybody for coming. It's great to have you here. It looks as if we may have another question. Let me just have a look. June says, "Did Paul ever meet Carl Sagan?" You have been called the contemporary Carl Sagan, haven't you, Paul?
Well, thank you. That's quite flattering. Carl Sagan was a great writer, and I was very inspired by him. Unfortunately, I never actually met him in person, but he wrote beautifully. So I'm very humbled to read his writing, and even to be put in the same category is very humbling and flattering.
Oh, it's lovely. Yes, I remember every week. I think it was on a Wednesday back in the late 70s, 79 or something, when Cosmos was on TV once a week. And I used to be eagerly waiting for it to come on so that I could watch it. It was the only program that I made sure I had time out for watching. Vince, thank you.
Another popularizer, Isaac Asimov. I met him when I was a teenager. He gave a lecture in my neighborhood, and that was quite an honor, because he wrote so many great science and science fiction books. Oh yes, he was one of the masters of science fiction, wasn't he? Incredible writer, and lovely. Okay, well, thank you very much for coming, and thank you everybody for joining us. Thank you, everybody. I hope you've enjoyed Paul's presentation. I have recorded it, so I will put it on YouTube once it's converted and uploaded, and I'll share the link on Paul's public Facebook page, and Paul will share it on Twitter. Thank you so much, Lisa. Thank you, Paul, and Jesus, thank you. Very interesting presentation. Okay, well, goodbye, everybody, and thanks again for joining us, and thanks again, Paul. Bye.